Welcome. My name is Patrick Curran, and along with my highly reliable friend Greg Hancock, we make up Quantitude. We are a podcast dedicated to all things quantitative, ranging from the relevant to the completely irrelevant. In this week's episode, Greg and I take a walk down memory lane to rediscover classical test theory, although we revisit this through the lens of modern latent variable models. We describe how these classical methods are actually highly restricted latent measurement models, and we explore how these restrictions can be relaxed and even tested. Along the way, we also discuss weird dates, free Tupperware, yellow fatty beans, advice cookies, in bed, scalloped tiles, scales at NASA, important footnotes, working in your garden, being buck naked, the dark side of the moon, squarshing, deserving variance, and when the cops show up. We hope you enjoy this week's episode. Is it in any way weird that I thought of you while out on a date with my wife?
It is in every way weird.
Yeah, that's kind of what I was thinking.
Dare I ask?
So my wife and I went out for dinner to a Chinese restaurant here in Chapel Hill. It's a lovely place, one of our favorite ones to go. Indeed, when we were first-year assistant professors, we went to the same place. We would go there when we were running out of Tupperware because they have these really nice to-go containers.
It's so practical, and it's all matching. I think we still have some.
It's matching, it's high quality, and it's free.
Yeah.
We have this lovely dinner. One of my favorite things, and it goes back to the earliest days when I was a kid, we got the fortune cookies. There's a double reason that I thought of you. First, I remember you used to collect fortunes, if I remember.
It is absolutely true.
And the second, I'm going to be old man Grandpa Simpson.
And that's why today, bananas are called yellow fatty beans. Question?
Back in my day, fortunes used to actually be fortunes, where now they're just statements.
It's true. Or advice cookies.
They're like advice cookies. You should have a lovely dinner, get some replacement Tupperware, and say, all right, let's open our advice cookies.
Have you done the thing where you put in bed at the end?
Yeah, when I was 8.
Oh.
Yes, and so I'll do this. I'm holding the fortune right here.
All right.
My fortune reads, a faithful friend is a strong defense. In bed.
So I have to have clarification. At what point in the fortune were you thinking about me?
Yeah, there's no reason to dig deeper than I've already given you. That's it.
Okay.
That's not a fortune. Let's leave the in bed part off. I don't care about a faithful friend as a strong defense.
I don't know if you've ever encountered this, but they have these things called misfortune cookies. I don't know if you've heard of those. There's one I remember that says, things will get better. Sometimes. Maybe. So the whole fortune cookie thing for me actually started in junior high because I used to tutor friends of mine who wanted help. And this one kid worked at a Chinese restaurant and he wanted to pay me something for tutoring him. And I said, you don't have to do anything. But he would bring me these giant bags full of hundreds of fortune cookies. And so I had them in my locker and I would go in there between classes and open up a fortune cookie. And then I would just have this stack of fortunes piling up in my locker. And I didn't collect them exactly, but it was such a routine part of my day in junior high. And then when I was in grad school, I ate at a Chinese restaurant, the same Chinese restaurant, almost every single day. And the reason was that they let me reuse a coupon. That was it, right? I had a coupon and I would go there and the lady would say, just keep it, bring it back tomorrow. So at the end of the meal, I would get my fortune and I would open it up and then I would go back to my office in grad school and I would tape the fortune to my desk. So over the years, I had hundreds of these fortunes taped on the surface of my desk, on the sides of my desk. And it seemed like the coolest idea until when I finished, my advisor told me I had to clean them all off of the desk. And they were all taped down. And so every single one I had to like scrape up and there were hundreds. So it was a horrible idea. But there was one that I saved, and this is absolutely true. There's a copy of it on my office door to this day. And I liked it because it's very appropriate to things that you and I think about now in our lives. And that fortune says, Love truth, but pardon error. Now, do you know why that makes me think of what we do?
It makes me so sad that I do. And that is classical test theory.
Yeah, that's exactly why I hung on to it. To be clear, I did not ever, until this moment, add in bed on the end of that.
Ooh, try that. Go ahead.
Okay. Love truth, but pardon error in bed.
It works every
I just
time.
don't know how I feel about that. I don't know how I feel about that. The place where you and I are, in terms of the modeling, in terms of the contributions that we've tried to make to our field, really revolve around the problem of having error in the measures that we have. And classical test theory was the first attempt really at formalizing the idea of measurement error. And the problem for me is that we assume when we say things like classical test theory in a class that we're teaching, right? Might be teaching a regression class, might be teaching another class, SEM. And we say classical test theory, we just sort of toss it at the class as though everybody knows what that means. And then I go back and I think, okay, wait a minute. Do they actually know what that means? To me, this feels like one of those things that might actually fall through the cracks for those people who aren't students in our own programs.
When you and I came up as grad students, this was core stuff.
Oh, yeah.
This was Cronbach. This was Cooter and Richardson and Spearman and Brown. And observed score was true score plus error. And I mean, it was woven into the fabric. And I feel like in a lot of places, not everywhere, obviously, but in a lot of places, you kind of jump over the classical test theory and you go right to these latent variable models and you do what you do. A lot of times we don't give a strong foundation in classical test theory. We go to the latent variable models and then people compute means and report coefficient alphas, which is classical test theory.
Yeah, you're absolutely right. And I wish people didn't skip over that stuff. But one of the cool things for me is that even though they make that leap, the latent variable framework is a framework for understanding classical test theory. And so what I was hoping is that we could take some of the just most basic ideas of path models and latent variables and use that as a way to backfill some of the classical test theory stuff that people just might not be aware of or might not have an understanding of.
And even if they have been exposed to it before, by skipping over the classical test theory, which is equation-based.
Yep.
It's obtuse and it's obscure, and I teach this stuff. So I think a picture way of thinking about it is super helpful. It is not dissimilar. What did I say in the confidence interval episode? I said, I don't want anybody to email me some YouTube video that explains the phases of the moon. I could not have been more clear. I can't describe to a 5-year-old why the moon is a crescent. All right, now, before you email me a website that describes it, I want to clarify, I did go to 5th grade. I have one of the best undergrad students I've worked with in my entire career, Suryaduti Baral. Greg has met Suryaduti.
Yep, terrific guy.
He is a 1 in 1,000 kid who is finishing up his undergrad and is moving on to grad quant programs. He's doing applications right now. He sent me an email with the following YouTube clip.
The phases of the moon are 888. Let's see what they look like.
All right. In fairness to Suryaduti, I kind of understand the phases of the moon now. So what I'd like you to do, Greg, is give me the equivalent of the phases of the moon video in path diagrams.
All right, I will try to do that again in an audio medium.
5 years, we still haven't figured that out.
No, it's what we do.
Anyway.
All right, let's lay some foundations. And you are absolutely right. It is equation-based in its origins. And that's what you and I went through, all of the derivations in grad school. The point that I want to make is that there's an easier way to think about it that winds up yielding the same things. It takes work. It just takes different work. But I just like it so much more because it ties really well in with all the other things that we have. So the first thing, what do we mean when we say we have a score on something? What's a score?
I don't want you to get too much of a clear image of this. Every morning, right before I get in the shower, I step on a scale, buck naked. It's digital. It rounds to the 10th, and I stand on it.
Okay.
And I just look and I go, ugh, shouldn't have eaten that pizza. And I get into the shower. That reading is the observed score. All right. But what is that? This is for real. I have these weirdo scalloped tiles in my bathroom where they're not flat. They have these little waves in them. And it's a digital scale that if you nudge it around with your foot, depending upon where those scallops fall, you actually get a little bit different reading. And so actually, if it's a little higher than I want, I nudge it with my foot and get back on it, and I nudge it and get back on it until I get a lower reading. Well, why is it a little higher sometimes and a little lower sometimes? That observed score that is on the numerical readout is an additive combination of my true weight. If I went down to NASA and got on their true weight scale, there is a true score, but there is a random error component to that. That's kind of where it falls on those scallop tiles. So the cornerstone of classical test theory is my observed score Y is a sum of true score T plus error E. Y equals T plus E.
If we go back to the origins of classical test theory, just the use of the word test gives you a sense of where this came from. Spearman, our friendly footnote founder of factor analysis.
Yeah, in a table in an appendix. Oh, by the way, I'm going to change the entire face of scientific research, but I'm going to bury it in the footnote to a table.
So he actually is considered the founder of classical test theory in the following sense. He thought that any test that we administer to a child, which yields a score, so we get a score for kids on math ability or perception, whatever the heck he might be measuring, he described every measure that we get as fallible measures of human traits. And he has this quote where he says, "By practical observation, we evidently do not obtain the true objective values. When we gather information on a score, which you have called Y, the idea is that that isn't necessarily the true thing that we're aiming for. It has some fallibility associated with it, and that fallibility you described as error, or measurement error, as we call it."
I really like how you threw the original lifeline back to Spearman, because Spearman is widely credited with the original development of factor analysis, but with classical test theory. When you talk to people in the field, he's often not given the credit that is due.
Yeah, and if you go back to stuff he wrote sort of in the 1904 to 1913 range, he was really wrestling with this stuff. And so his name should be attached to a lot of the origins of this. And as you said, there is this most fundamental equation, Y equals T plus E, where Y is the observed score, T is the... How would you define T?
True.
Okay. Yes.
True.
True. Okay, so in your example of the bathroom scale, T would represent your true weight. And then E is essentially like the remainder. It's like the leftover stuff. It's the difference between your observed measure, Y, and whatever your true value would be on that. A way to think about that true value, by the way, is if you moved your scale around to all the different possible scallops that you could have in the floor of your bathroom, right? An infinite number, and then took the average of all of those measures, then you would have what we would consider to be your true score. A distinction that some people like to make is that could be different from your true weight. A true score being a long-run expected value of the score that you could get is not necessarily the same thing as a true representation of whatever it is you are trying to measure. The example being, if it's the case that your scale just flat out weighs heavy, if it'll make you feel any better, let's assume that your scale just weighs 5 pounds heavy. You could move your scale around to all possible locations on the bathroom floor, get every possible reading, take an average, and you would have some representation of T, which would be your long-run expected average of the scores that you would have, but it wouldn't represent the construct we're interested in, which in this case would be your weight. Spearman initially differentiated between T as a representation of the true trait that you're interested in versus T as a representation of the long-run average that you have. Now, if we assume that your instrument has no what we could call systematic error to it, your scale does not have a tendency to weigh heavy, your scale does not have a tendency to weigh light, then it would be the case that the long run average of all of your weight readings across all of the different places you could locate your scale would in fact be your true weight. And then the error, which is just the difference between those, is just some plus or minus random nudge on top of truth that gives you the specific reading that you have. All right, so now what I'd like to do is I'd like to take the fundamental equation that we have here, y is equal to t plus e, the observed score is equal to truth plus error, and I'd like to take that and represent it in a path diagram. And here's the way we can think about it. I'm assuming that everybody out there is somewhat familiar with path diagrams, and dear Lord, if you've been with us for all of the episodes, you should have some familiarity with it. Let's think about the true score as a latent variable, something that we don't directly observe. And it is a T with a circle around it on our whiteboard. We have Y, which is the observed score, in a box. And what are the things that are pouring into Y? Well, T, the truth, and then the stuff that's left over, the error. So I have the latent truth coming in with a path of 1, and I have the error coming in with a path of 1, right? So it is 1 chunk of truth plus 1 chunk of error. That's just a graphical representation. Now, the really cool thing about this particular picture is that it conveys things. For example, as path tracers, we could ask, according to this representation, what are all the reasons that the true score and the error score are correlated with each other? And I look at a diagram like this and I say, well, I can't actually trace my way from truth to the error. If you want to use language of colliders, that's because Y is a collider. You can't trace your way through Y. So this diagram represents one of the core assumptions of classical test theory, and that is that your true score and your error score are completely uncorrelated. That's just right there in this picture.
My brother is listening right now, and he's working out in the backyard on his garden, probably preparing it for spring planting. And Dan, this is not just a pencil neck, egghead thing on the whiteboard that we're working with. Think about, in your business world, employee reviews, index for inflation, expected return on investment in a particular domain. This thing impacts every single thing we work with. A GPA, a GRE, an SAT, whether you look at any kind of index in polling for presidential nominees. All of these things we can conceptualize as an observed value that is some combination of the true value plus random error.
Mm-hmm.
So I'm just trying to keep my brother engaged as he's working out in the garden.
All right. Hi, Dan. All right. So this model, in the language that you and I are accustomed to using, we could say this model has a covariance structure associated with it. This model implies why the variables vary and covary the way that they do. And in this model, T, truth, is an exogenous variable. E, error, is an exogenous variable. So those will have variances that are part of this model. Y, the observed variable, is endogenous or dependent. And in fact, if we said, based on this model, what should the variance of Y be equal to? That's just a path tracing question. And we can trace our way from Y up to T and back, and we get the variance of the true score. We can trace our way down to the error and back and pick up the variance of the error score. That means that the variance, according to this representation, the variance of Y is equal to the variance of truth plus the variance of error. How much people vary naturally on the observed score is a simple sum of how much they vary on the underlying truth plus how much they vary on error, or the noise that is added into the system.
Now you pulled a total Penn and Teller there.
Please welcome the masters of magic, Penn and Teller.
Because everything we talked about was my reading on the scale. All right, wise guy, how am I getting the variance when I have my weight is the true score plus the error?
Yeah, you're right. I am hiding things from you in two ways. One is I can't get your true score unless I ask you to do an infinite number of bathroom readings, or I ask you to go to NASA, which, by the way, is located in Greenbelt, Maryland, just off the Parkway.
So I could drive up buck naked, get on their NASA scale, and drive back buck naked and get in the shower? Score!
I'm just concerned when you get out to fill up your tank along the way. Yes, so that's right. So we don't have true scores for people, but if you think about it across individuals, there's variability in people's true weights, just as there's variability in people's true math ability. There is resulting variability in their observed scores that we have for weights, just as there is observed variability in the scores that we have, like math tests. And then there is error variability. So you are right that right now this is really just standing as something conceptual. And if we think about it from an identification standpoint, this is underidentified because Y only brings one variance to the table. And what we're saying is that through the magic of this representation, the variance of Y breaks apart into true score variance and error variance, but I can't make two things out of one. So as it stands right now, this is underidentified in its covariance structure.
And think about it as a parallel. My weight that I observed is the sum of true plus error. Okay, so weight equals T plus E. Imagine that I am 183 pounds and I give you an equation, 183 equals T plus E. Please solve.
Exactly right. That is a really useful other way to think about this as an identification problem, because what you're saying is that something observed is the sum of two things that you didn't observe. Now, under identification notwithstanding, this is already a useful way to visualize this model. It's a useful way to think about the implications of this for the assumption that the error and the true score do not correlate with each other. It's useful as a way to think about that theoretical decomposition of the observed score variance into true score variance and error score variance. And then there's also a mean structure that goes with this. Now, sometimes we represent mean structures as a little one in a triangle with paths coming to everything.
Dark side of the moon, baby.
Ooh, I like it.
Taking away the moments that make up the dull day.
So when we have a mean structure in a model and we represent it as paths from a one in a triangle coming to the different elements in a model, when that's coming to an exogenous or independent element in the model, it represents a mean. So when I have a path from the one in the triangle coming to T, the true score, then that represents the mean of truth. So whatever our average true weight is, whatever our average true math ability is. When I have an arrow from that going to error, which I never do, the reason I never do that is because we assume that the mean of the errors is zero, that sometimes errors are up for people, sometimes errors are down, sometimes the scale gave them a high reading, sometimes the scale gave them a low reading, that all of that balances out. So in just about every diagram you have ever seen with a mean structure, there wasn't even a path represented from the symbolic one in a triangle to the errors because we assume the mean is zero. The absence of such a connection here is a formal statement. It's kind of implicit, right? But it's a formal statement that we think that the errors cancel out in the long run. We also often will have paths from the one in the triangle coming into the dependent variables or endogenous variables in our model. In this case, there's only one endogenous thing, that is our observed score Y. That would represent an intercept. In this model, what that would represent is if there is any systematic error in the measure that we have. So if your scale was weighing 5 pounds heavy all the time, then that means that your long-run average score for weight would be a function of your true weight and that extra 5 pounds that's coming in. But if we assume that there is no systematic error whatsoever in our measurement, which is an assumption, right? That it might be an unpalatable assumption, then we would not have any need for a mean structure path coming into the dependent variable. If we don't represent that, then we assume that is zero. So that means that the picture in the end captures the idea that the long-run expected value of your score Y is just whatever the average true score is with nothing else added. No additional systematic error. Some people refer to that as bias. There's no bias in this scale. So this picture captures a lot of things that are just foundational for classical test theory, either in terms of what is represented in the model or what is not represented in the model.
The main thing I would reiterate at this point in the conversation is the fundamental assumption that the errors are random.
Yes.
This is critical in a lot of what we do, but particularly within classical test theory. Imagine my scale and my scalloped tiles that if you weigh more, the impact of those scallops on the measure is less. that you squash it down and no matter where you toe it around to get a different weight, it comes up the same. But if you're much lighter, the little scallops have more of an effect. And if you nudge it around with your toe, that you're going to get differential reading because you're not squashing it flat against the floor of the bathroom. Those would be non-random errors, and that would be a violation of this fundamental assumption.
That's a great example, right? And that even suggests that there might be a connection between truth and error, such that the higher your true weight, the lower your error due to the squishing. The lower your true weight, the higher your potential error due to a lack of squishing.
It's squarshing.
Squarshing? Really? Okay.
Dude,
all right.
Did you prepare it all for today?
Okay, now that we have this graphical representation, which we are accustomed to calling a model, with all of these properties that it conveys to us, both explicitly and implicitly, things just build out from this so beautifully. For example, how do we usually define reliability in terms of variances?
We can think about reliability as the ratio where the numerator is true score variance and the denominator is the total observed score variance.
Exactly. Where that observed score variance down there in the denominator could further be broken up into the parameters that we have in the model, which are the variance of the true scores plus variance of error scores. So reliability comes directly from this model as the ratio you described, but also as a function of the model parameters that we have. What this also means is the error variance can be thought of as the total amount of variance in the observed scores times how unreliable your measures are, right? 1 minus the reliability. And we even take the square root of that in classical test theory to get something really useful called the standard error of measurement.
And this is a very logical index because what if the true score variance equals the observed score variance? Well, the same thing in the numerator and the same thing in the denominator equals 1. There's perfect reliability because there is no measurement error if true score variance equals observed score variance. But as that begins to fall off, and now it becomes 90% of total variability, 80% of total variability, then we start working in, well, you don't deserve it. This is how sometimes I think about it. You observed variability on your math tests, but you don't deserve all of that because part of that is true and part of that is random error. You don't deserve all of it. You only deserve the proportion that's true.
I like that. So let's take this basic model and expand it out. And we're going to do one little expansion, and then we're just going to imagine a much broader expansion. Here's what I'm going to do now. I'm going to have everybody step on their bathroom scale one time and then a second time. Now, rather than having just one y in our model, we have two y's. We have y1 and y2. Now, the assumption here is that there's the same true score that underlies each. So I have y1 dependent on truth plus error. And I have y2 dependent upon the same truth, the same t in a circle, plus its own error. So in this model, the paths coming into y1 and y2 are both 1 because they're each one chunk of the same truth, and then they get one chunk of their respective errors. Now, in this model, if I ask myself, how are those two errors correlated or covariating with each other, my path tracing skills say they're not. There is no way for me to trace from error 1 to error 2 in this particular model. Once I trace my way back to y1 or trace my way back to y2, I can't leave anymore. So this model conveys the assumption that whatever error we have in the first measurement is completely independent of whatever error we have in the second measurement. Are you okay with that so far?
That's spot on. And that goes to the point of random measurement error is when we think about a covariance or a correlation, we can ask ourselves colloquially, does knowledge about one thing tell us in any way about the other thing? And this model is saying absolutely not. If you give me your error on the first measure, that tells me nothing about your error on the second measure.
That's right. Completely independent of each other, or so we assume in this particular model. But your point is really terrific. We can imagine scenarios, maybe not with bathroom scales, but if this is a math test from time 1 and time 2, and people are fatigued, or there are environmental conditions. The room is really cold and people aren't doing their best, right? You could imagine that there are some of the same things that are operating to nudge scores in a similar direction. This model assumes that that is not the case. Now, path tracers, if I asked you in this model what the correlation, not covariance, the correlation between Y1 and Y2 is, you could use all of your path tracing skills to figure out the correlation between Y1 and Y2. And they would be correlated, right? If two scale readings or two math test scores have the same underlying true score, then we absolutely would expect that the two measures are going to be correlated to some extent. Well, when I path trace for correlations, one way to think about that is the definition of a correlation is the covariance between the two things that you're correlating divided by the standard deviations of the two things that you're correlating. So imagine, first of all, to get the correlation between Y1 and Y2 based on this figure, I trace my way from Y1 up to T across a path of 1, and then I trace my way down a path of 1 down to Y2. Product of those is just 1 times 1, and in that trace, I pick up the variance of the true score. So the covariance between Y1 and Y2 is nothing more than the true score variance. So the correlation between x1 and x2 is the covariance in the numerator, the standard deviation of y1 times the standard deviation of y2 in the denominator, the standard deviation of y1 times the standard deviation of y2. If those are two measures that are assumed to be completely equivalent, right, two bathroom scale measures, then the standard deviation of one should be the same as the standard deviation of the other. And so what we should have in the denominator is just the variance of a scale reading, the variance of a math test, the observed variance. So I have the observed variance in the denominator. I have the true variance in the numerator. And what you can see is that the correlation between two measures is a way to think about the reliability, because that comes out to be the ratio of the true score variance on top to the observed score variance down on the bottom. And so when we talk about test-retest reliability, it seems like there's this weird disconnect where we go from, wait, I thought reliability was a ratio of variances, and now you're telling me that it's how one thing correlates with itself across two administrations. This picture shows exactly that the correlation between Y1 and Y2 becomes the ratio of true score variance to observed score variance, which is by definition reliability. So this picture shows us how reliability can be conceived of in at least two different ways.
Which we will add to the list of reasons why people hate us. What is reliability? Well, it's the ratio of true to observed. Oh, okay. What is reliability? Oh, it's the correlation across your test. Oh, but these are equivalent ways of thinking about the same thing.
Yep. And for me, I love the beauty that just comes directly out of a very simple visual representation of things.
That's right. And this is a big part of our discussion, which is classical test theory is not devoid of latent variable modeling.
That's right.
We can embed them within. This is just a way of saying, wait, we're all to varying degrees exposed to latent variable models and to varying degrees can navigate path diagrams. Let's use these to recast the classical test theory model. And then you have been holding those paths to one that link true to y. We don't gotta.
That's right. That should be a source of discomfort, a source of us hiding some things from you, because the picture that we have just now has held a lot of things constant. And the model that we've had so far is sometimes referred to as a parallel model for a couple of reasons. One is that we have that true score contributing equally to both of those variables, which I'll tell you what, I have no problem with when it is weight from a bathroom scale. That makes complete sense. I have a true weight, right? And if it's the case that I could give you the same math test twice and wipe your brain from one time to the next, then I like the idea of you having a true math ability that is trying to express itself into both of those, the same true math score. I like that. But the practicality is that we can't really administer the same test twice. And so what we do is we measure some other test of math ability and we kind of hope it's the same. And that means that we assume that there is some true score that contributes equally to two different measures, literally two different math tests. And it starts to get a little bit uncomfortable. So everything that we have talked about so far has assumed equal contribution of the true score to the two measured variables that we have. And it has assumed the same amount of error variance contributing to both of those. And this is sometimes referred to as the parallel model. And Spearman, right, back in the early 1900s, made a great observation. He said, the correlation between two scores will be found a useful measure of the accuracy of the observations. And he was using accuracy as a representation of reliability. But that assumes things are constant. And so we could imagine this model being expanded in a couple of ways, specifically where the constraints are. We've got a two-variable model with y1 and y2. The paths from the true score to each of those is currently assumed to be the same, and the variances of both of the error terms for y1 and y2 are both assumed to be the same. Let's go back to our bathroom scale. Don't imagine that naked Patrick.
Think about me buck naked, ready to get into the shower.
Oh, God. At all costs, avoid imagining naked Patrick taking a weight measurement with his scale in one location on the floor, where the scalloping of the tiles gives him a little bit of fuzz in the measurement, and then he moves the scale to some other location. So it's the same scale. I expect that his true weight is contributing to the reading on each of those to the same degree, but now he's in a different location on the floor, so there's a different scalloping to the tile. The tiles might be a little bit more uneven in that location, giving a little bit more error in reading. I don't know. But the point is that we could imagine a model where the true score is contributing to both of the scale readings to the same degree, but the error variance isn't the same. And the way I described it was there were contextual reasons. The context happens to be naked Patrick's bathroom floor. But if these were other types of measures, like the same math test administered at two different points in time, but maybe one of those times is the morning and one of those times is in the afternoon, you might expect that both of those are measuring the same underlying true score to the same degree, right? True math ability contributes to y1 and y2 to the same degree. But there are context reasons that might be affecting the amount of error, right? The noise that's in the system in the morning administration as opposed to the afternoon administration. So now we have an example where the two loadings, if I want to use the factor analytic term, the two loadings are the same for y1 and y2 on that true underlying factor, but the error variances are different. This is no longer a parallel model. This is referred to as a tau equivalent model. Tau equivalent model is a model where the underlying truth contributes equally to all of the measures that you have, but you potentially have different error variances. And it's called tau equivalent because tau is sometimes used to represent truth or the true score. So the true score is contributing equivalently to each of the time points. Well, that's a more flexible model. That's a bit more realistic. But honestly, only a bit more realistic in some scenarios. Sure, if I'm using the same bathroom scale twice, or if I'm giving the same math test twice, then I might be comfortable with thinking about the loadings being the same. But what if I use a different bathroom scale? I have a really expensive bathroom scale, and then there's another cheaper bathroom scale in Patrick's bathroom. But he's a guy who likes to gather more data, so no more naked Patrick. Patrick steps on one scale, gets his reading, steps on the other scale, gets his reading. What I don't know is that the true score is equally manifesting itself in each of those different measures, right? So the idea of T coming into Y1 and Y2 exactly to the same degree, that's a little bit harder for me. Certainly, if I have two different math tests, right? Math test 1 and another math test, which is meant to cover the same content, but I'm not sure at all that true underlying math ability is able to manifest itself completely equivalently in Y1, the first math test, and Y2, the second math test. So an additional flexibility that we could imagine having is moving from the tau equivalent model, which had equal loadings, equal contributions from truth, to a model where the variable's loadings on that underlying factor, or said differently, where the contribution of that underlying true score to the different measures is potentially different, or said in factor analytic language, the observed measures that we have, Y1 and Y2, potentially load differently on that underlying construct. That, for my money, is probably the most realistic scenario. where you have potentially different error variances for each measure, and then you have potentially different loadings for each measure. And that is a situation that is referred to as a congeneric model. And for my money, the congeneric model is far and away the most realistic, right? Because imagine now you expand beyond having only 2 tests. In fact, let's think about it differently. Let's think about it as you have one test, but that test is made up of a bunch of items, 10 items, 20 items, and we could think of each of those items as though they are their own little test. And not all of those little tests will have exactly the same truth that underlie them. And you know this as a test taker because when you get to item 14, you're like, yeah, I have no idea, right? Your true score on item 14 doesn't look the same as your true score on, item number 3. So the idea that there's this common truth that pours equally into all of those is very unpalatable.
On my side of the street, in psychology, this gets particularly important. In my kind of work, I have 5 items of depressive symptomatology, and one is sometimes I feel lonely even when I'm around my friends, and another is I often fantasize about hurting myself. Mm-hmm. Now you start thinking, wait a minute, that assumption that those 2 items are equally indicative of the underlying latent factor is very hard to swallow. And moving from a tau equivalent to a congeneric kind of view is critical. It's not just an assumption that's handy and tidies up things. I want to be able to build that into the model.
And here is the complete beauty of the representation that we're talking about right now. One is there are many equations that fall out of the picture that we have. For example, for those of you who have heard of the Spearman-Brown prophecy formula.
In bed. Sorry, it just sounded like a fortune.
How much more reliability would you have to an instrument if you added one more item in bed?
It works. It actually works.
Totally works. But that's the idea behind the Spearman-Brown prophecy formula is that if you add another item to a test, add another item, how much would you expect reliability to increase? That formula falls ever so beautifully out of a model, but it is a model where everything is parallel. You have all the loadings the same, all the error variances the same. And if that's not true, which, oh, by the way, it's almost certainly not true, then what use would that formula be specifically? So as Patrick said, we can express all of these things in models. So now you're someone developing an instrument, you can test these models. So if someone said, yeah, I would like to know whether or not a parallel model captures the relations among these items, among these observed scores. Well, use your confirmatory factor analysis skills. Freeze all the loadings to be the same. Freeze all the error variances the same. Run it, and I'll tell you what, it is going to slap you right in the face because there ain't no way, no how you have a parallel model. You can also run a tau equivalent model where you free up those error variances and you run it again. You can check the fit of that model by itself. You can check the fit of that model relative to a parallel model. And oh, by the way, that's what Chromebox Alpha assumes. Chromebox Alpha assumes a tau equivalent model where the contribution of the underlying construct to all the individual items is the same. It allows for different error variances, but it assumes those other things are all the same. Is that palatable? I don't know, right? I could say, well, I assume that is the case. Forget assuming it. Run the damn model. You can do it right here in a confirmatory factor analysis framework. But you can also run a congeneric model. You can run a model where you say, okay, I'm going to free up the loadings also. Get the fit of that. Compare it back to the tau equivalent model. Look at the fit by itself. That will give you a sense of how egregious the assumption is that underlies a Chromebox Alpha and moves you into a congeneric model. So this isn't just some academic exercise. This is setting a framework for you to actually be able to test the assumptions that underlie the instruments that you have very explicitly.
And as you're implying, these are nested within one another.
That's right.
Which means that we have likelihood ratio tests. You can make a formal inferential test of paying the reaper, right? Which is if I have these all be equal or if I allow them to differ, is there a significant improvement in my ability to recreate the characteristics of my sample data? It becomes a testable hypothesis. And what you said brings me to one of my favorite quotes. You called it Chromebox Alpha. It is Chromebox Alpha. It is widely referred to as Chromebox Alpha. But Chromebox wrote later in his life that he shouldn't have his name attached to it.
Yeah.
It's just coefficient alpha.
Yeah.
And I scribbled out one of his quotes that I love. To make so much use of an easily calculated translation of a well-established formula scarcely justifies the fame it has brought me. It is an embarrassment to me that the formula became conventionally known as Chromebox Alpha. I just love that.
That's nice.
The cops are showing up and Chromebox is like, I had nothing to do with this.
If he had gone the distance, then he would have said, in fact, Gutman wrote about it several years earlier.
Well, this is kind of a non sequitur, but the historian Steven Stigler has long talked about, what is the phrase he uses, misonomy? How virtually nothing in science is named after the person it should be named after. And Chromebox Alpha is a great example of that. But regardless, our friend Dan McNeish at Arizona State University was shopping one afternoon and wrote a psych methods paper in the produce aisle that gives a lot of discussion. It's something along the lines of, thanks coefficient alpha, we'll take it from here.
Yeah.
We routinely use coefficient alpha without maybe appreciating the price to get on that ride in terms of assuming tau equivalence when maybe that doesn't hold.
That's right. And again, the beauty of this framework is that you can test whether or not that assumption is reasonable, whether you would reject tau equivalence in favor of something being congeneric. And we've talked about this all the way back on season 1, a measure of reliability that is specific to the congeneric framework that's more flexible is now am I allowed to say it's McDonald's? I think it's McDonald's. McDonald's omega. Coefficient omega. We'll call it coefficient omega, which assumes a congeneric model. Now, the funny thing about Dan's paper is that he got some backlash about that, where people wrote and said, it's good enough. Chromebox Alpha is good enough.
Back in my day,
we did alpha, which was the style of the time.
and that's the way we likes it.
We liked it. A way to think about that criticism, to be fair to it, is that if you think about the generalizability of things, right? When we compute an omega, we are tailoring it to the very specific loadings that we get in a given sample. But if we gathered another sample, another sample, another sample, those would be going up and down. So the cost of it might be sort of a hyper-tailoring of that index to a specific sample, whereas Chromebox Alpha just throws a 1 on there or an equivalent loading that says, it'll all come out in the wash. So that was really the criticism. That said, I'm not a huge fan of using the wrong model when we're assessing reliability.
When you're working with factor analytic models, you are working with classical test theory as a starting point, or at least you have the potential to. And then all the other kinds of models we do are very often nested within that and are testable hypotheses.
And not just are they testable, which I love. You can use the parameters in your models, whether it's a parallel model, which who cares, a tau equivalent model, or a congeneric model. You can use the parameters from that to compute whether it's Chromebox Alpha in the tau equivalent case or McDonald's omega. In the congeneric case, you can build it as an additional parameter based on the parameters from your factor model. And then, and we talked about this, I think, in the Annie's Flower Shop episode, you can bootstrap the heck out of that and get confidence intervals for it. I mean, it's all right there. So I think we really should start availing ourselves of this model-based way of thinking about the quality of our instruments.
In bed.
I
beat you to it. He leaned in and I beat him to it. All right, everybody. Thank you so much for your time.
All right. Take care, everybody.
Bye-bye.
Thanks so much for joining us. Don't forget to tell your friends to subscribe to us on Apple Podcasts, Spotify, or wherever they go to help them make sense of their errors. You can also follow us on Twitter, where we are at QuantitudePod, and visit our website, quantitudepod.org, where you can leave us a message, find organized playlists and show notes and syllabi, listen to past episodes, and other fun stuff. And finally, nothing says Valentine's Day love like the gift of cool Quantitude merch, like shirts, mugs, stickers, and spiral notebooks from redbubble.com, where all proceeds from non-bootleg authorized merch go to donorschoose.org to help support low-income schools. You've been listening to Quantitude, the podcast that the Spearman-Brown prophecy formula foretold would actually get less reliable the more we add to it. Today's episode has been sponsored by the fortune cookie game of adding in bed to the end of things to make them more interesting. Something statistics could definitely benefit from. So let's try it. Many senior researchers have been hit especially hard by a replication crisis. In bed. Researchers tend to prefer Satora-Bentler rescaled maximum likelihood statistics because of their robust performance. In bed. In a Bayesian analysis, using a strong prior can end up giving you a really tight posterior. In bed. In a DSEM, if the period of time is too small, things might not be able to be very dynamic. In bed. And finally, when screening for outliers, you're generally looking for extreme deviates. In bed. This is most definitely not NPR. In bed.